So, how y'all doing? Fair enough. We are partway through test week. I presume everyone in the room right now hasn't taken it yet. So, once again, main focus of today is making sure everyone feels prepared. So we'll focus primarily on questions related to homework and practice tests and things like that from you guys. So what's on your minds?
Well, what formula is not listed on the formula sheet should we have?
I would say that all formulas that you would need are on the formula sheet. However, there are some additional useful facts that I think would be good to have. Things that I would recommend that you write include the mnemonic for the most common metric prefixes, kilo through milli, because you do have to make sure that all your units are in the correct version. SOHCAHTOA is handy. So there is a non-negligible amount of trig. And there's a few places where I recommended that you add absolute value brackets. For instance, on the GPE formula, since in this particular formula, we don't actually want a negative answer, even though we always make G a negative number, and that's because energy isn't a vector. It doesn't care about the direction that gravity points, it just cares that gravity is acting. So this formula is one I'd recommend adding absolute value brackets around if you haven't already. Another would be your force of friction formulas. Namely around the force of friction itself, because normal force tends to point up and force of friction can very often point in a negative direction, but this formula can't tell you that negative. Alternatively, if you plug in a negative force of friction into that formula with the goal of, say, solving for normal force or mu, then the negative will kind of carry through and won't make a whole lot of sense if you get a negative normal force or a negative mu. So, frankly, both of these two formulas, I tend to make sure I have the absolute value written there for context to make sure that negative answers don't end up not making any sense. And I'd say the most important thing to put on the formula sheet, if you haven't already done so, I was very specific about this on Monday's lecture, is the relationship between all the vectors required to hold an object in place on a slope. Namely, this triangle that shows how gravity, normal force, and the force of static friction are all trigonometrically related if an object is currently being held in place on a slope. The main thing to note there is that gravity and normal force are separated by an angle that is equivalent to the angle of the incline. Meanwhile, normal force is perpendicular to the force of static friction because normal force has to be perpendicular to the surface. Meanwhile, static friction has to be parallel to the ramp's surface. Realizing the ramp is suddenly very hard to see. So, box on an incline, three forces are combined to hold it in place. And this is how those three forces interact with each other trigonometrically. I would highly recommend writing that second triangle on your formula sheet, because that's one of those things that I had a hard time doing from memory as a physics major. You guys, I presume, aren't physics majors or attempting to become physics majors, so you should definitely write that down if I had a hard time doing it from memory. Yes?
And then the normal force is always gonna equal gravitational force unless friction's involved?
No. Normal force and gravity are not always equal and opposite. They tend to be if something is sitting on a flat surface, but they are not always equal, nor are they always opposite. They're not always equal because even in this case, you can add extra vertical forces, and normal force was only ever as much as it needs to be. So if I mentioned when we were talking about normal force, the example of standing on a bathroom scale and using the counter to kind of lift yourself upwards slightly. The weight read by the scale decreases when you do that, right? Even though your actual weight doesn't change, right? Like lifting on the counter doesn't decrease the amount of atoms in your body. It doesn't decrease the actual force of Earth's gravitational pull. What happens in that case is you're adding a second upward pointing force, and normal force doesn't have to work as hard to cancel everything out.
So then in that case, normal force would equal force of gravity minus that additional force, or negative force of gravity minus that additional
Correct.
force. Okay.
So here, normal force and the force you're exerting team up to cancel out gravity, proving that they're not always equal. Now, if you weren't doing this, normal force would have to pick up the slack in equal gravity, but it's not always the case. And furthermore, on a ramp, normal force is neither equal nor opposite to gravity, because normal force is always perpendicular to the surface making it, whereas gravity always points straight down.
And that's why in this case, it's gonna be force of gravity minus the static friction.
Well, it's not, technically speaking, the net force here would be force of gravity plus normal force plus force of static friction, all adding up to 0. But all three of these point in a different direction. So you can't set it up like this. You can't actually perform the operation like this because they all point in different axes. So technically, they all three add up to 0, but you can't actually use the formula like this. That's what the triangle is for. Triangle is meant to show that all three of these are related trigonometrically, and you could use, sine of this angle equals friction over gravity, or cosine of this angle equals normal force over gravity. Did I answer the question?
Yes. I was just trying to figure out the normal force's relation to gravity.
Well, technically speaking, normal force is not related to gravity. It's a separate thing that coincidentally is often equal and opposite to gravity. They are officially not related, but they often work together or work against each other. Officially, they're unrelated.
And then is the reason the net force is 0 because there's no acceleration?
Correct.
Okay.
Right now, these drawings and this net force are assuming the box is being held in place by friction and not accelerating. If it's not accelerating, net force is 0, no matter how many things are adding up into that 0. Yes.
Could you go over number 4 from the practice test?
Yes. The file appears to have closed itself on me, which is very rude. Number 4, you said? All right. Now, I will apologize, actually. Someone pointed this out to me last time and didn't have time to fix it before today. My answer key here is not complete. There's one or two lines of math that I just forgot to write down. So that's on me, I apologize. But I can work the whole thing out with you guys here. That makes it even harder to read. So here we have a sled being pulled horizontally along the ground. Another problem with this particular question actually is after I originally posted the practice test, I realized I never listed a mass in this question. I since uploaded a second copy that did list it, but if you downloaded the first one and then never downloaded the second one, why would you? I never mentioned it. Your version of this question doesn't actually state a mass in it. So for my work and for the second version I uploaded, I am assuming and listing that the mass of the object is 25 kilograms. The problem is unworkable without a mass. So if you have the earlier version, please write that down, and I apologize. So, someone is going to pull a sled of mass 25 kilograms along the ground at constant velocity horizontally across a snowy field. This person is going to pull with a force of 100 newtons, and whenever you're dragging something by a rope, just because of human height, the rope tends to sit at an angle. Very rarely do you pull something totally horizontally. The rope is going to sit at a 45-degree angle in this particular case, meaning that 100 newtons is not completely forwards, nor is it completely vertical. It's literally at 45 degrees somewhere between the two. That will become important. We are told what the magnitude of the force is and the direction it is acting. And we've got a few questions here. First is, what is the net force acting on the sled? I can determine an answer for that question without actually having to do any math. Why is the net force on the sled 0?
Because it's at a constant velocity.
Constant velocity, very good. It says right here, sled is being pulled at constant velocity, which immediately means acceleration of 0. And if acceleration is 0, net force is 0. We know there's forces present, but they must all add up to 0 for the object to remain at constant speed. So net force is 0 newtons. We're actually going to be using that to figure out what each individual force actually is. Next question is asking to simply identify every force that is present, every force that is part of that net force of 0. The 4 that I listed here are F rope, F normal, yikes, that's hard to read, FG, and F friction. Those are the 4 forces that I have identified that must be present in this scenario. Force of gravity must point down, assuming this takes place on a planet. And if net force equals 0, then there must be some force counteracting gravity, because if net force is 0, if net force wasn't 0, the object would accelerate in some direction, but if it is 0, there must be some force canceling out gravity. So, assuming that we're moving horizontally across horizontal ground, the ground would push up as the sled is being pulled into it by gravity. So, in this case, normal force and gravity should be equal and opposite. Again, they are not equal and opposite by definition, but coincidentally, general rule, if you are sitting still on flat ground or moving at constant speed on flat ground, net normal force and gravity should be equal and opposite, again, if the ground is flat. And if there is no other forces in the vertical axis. If it's just normal force up and gravity down, they will be equal and opposite. If there is more vertical forces, bless you, than just those two, they will be opposite but not necessarily equal. Because normal force only acts as much as it needs to. Now in this case, normal force and gravity should be equal and opposite. Oh, actually no, they won't be equal. I got ahead of myself. Because there is a second vertical force here, but I'll show the math for that in a minute. There must be some normal force though, because we are going to be pressing into the ground is going to press back. So normal force would be here, and so part B just identifies that. Also force of gravity, because assuming this takes place on Earth, Earth's gravity will pull it down. The force in the rope is going to be acting. And lastly, even though snow is pretty slick, and even though sleds are pretty good at sliding across the snow, you cannot eliminate friction. And in fact, there must be some amount of friction in order to guarantee that the net force is zero, because we are pulling the sled forwards. There is an X force pulling this thing forwards, meaning if there wasn't friction, there'd be no force to cancel that out, and we would just constantly be accelerating forwards. If the net x-axis force was forward, we wouldn't be moving at constant speed. In order to move at constant speed, there must be some force backwards to equal out with the force forwards. And the most likely candidate here for that is friction. So I've indicated force of friction backwards. The question, if we are pulling the sled at constant velocity, what type of friction would that be? Kinetic, very good, because the sled is moving. So those are the identities of the four forces I have identified here. Any questions about any of their individual involvements? All right. Now part C is taking those identified forces and determining the magnitudes of all of them. We do know the magnitude of the force in the rope, 100 newtons. However, it's pointing at 45 degrees, and before we are able to use that information anywhere else, we do need to divide it up into its X and Y components so that we can use those legs and as contributions to each of those separate axes. So over here, I just did a little bit of trig. Apologies for my awful handwriting. Sine of 45 is the Y leg over 100, and cosine of 45 is the X leg over 100. So F rope Y is 70.7 newtons up, and F rope X is 70.7 newtons forward. They're the same number because that's how 45-degree triangles work. It'd be different numbers if it was any other angle. Again, sorry for my bad handwriting. Once again, F rope Y and F rope X. So those are the components of the applied force. Looking at the x-axis, there's only two forces acting in the x-axis. You've got the x component of the rope pulling forwards and the force of friction pulling backwards. And we know from our earlier assessment, net force in either axis must be zero. So net force X must be zero, and these are the two forces that comprise the net force in the x-axis. You've got the rope's X component forwards and the force of friction pulling backwards. And if two things add up to zero, they must be equal and opposite. So if we are using 70.7 newtons to pull the sled forwards, friction must be acting with 70.7 newtons backward to cancel out net force of zero, net acceleration of zero, moving at constant velocity. Questions about this idea? All right. Now, the part that's missing is analyzing the y-axis to determine normal force. Right here, I did use the weight formula to find the weight of the sled, force of gravity, so that's where the negative 254 Newton force of gravity comes from. Again, the thing that is missing, the calculation that's missing here is that of normal force. So to show that, to find normal force, which acts in the y-axis, man, all of my markers are dying. I feel like I just got half of them. Analyzing net force in the y, like we analyzed the net force in the x over here. There's 3 y-axis forces though, because you've got normal force up, gravity down, and also the y leg of the rope force up. So there's 3 things here in the y-axis. Now of those 3, gravity has a specific definition already. We know it, we can find a number for that. Bless you. And we've already determined the value of the y leg of the rope force. So normal force is the only unknown left here. We can use this analysis to determine what normal force would need to be. And again, it is opposite gravity, but it will not be equal to gravity because of the interference of the y component of the rope. So continuing on and trying to be mindful of positives and negatives. N minus 245, because gravity points down, plus 70.7, since the y leg of the rope force points up, equals 0. Therefore, N minus, add these 2 numbers together, minus 174.3 equals 0. Therefore, normal force must be positive 174.3 newtons. Again, opposite gravity, but not equal to it, because we are technically pulling upwards via the rope pointing at an angle. So again, this is kind of like if you're standing on a bathroom scale and you use the counter to lift yourself upwards slightly, you are reducing the amount of force that the scale has to exert to hold you up. So the normal force drops, and therefore the number on the scale drops, because the scale can't actually tell you, the force of gravity on you. It just tells you the normal force it is exerting on your body, because the scale doesn't have an understanding of mass times 9.8. The scale just knows how hard you're pressing into it. Same with the vertical hanging scales in a grocery store. It doesn't actually know how many atoms are in your broccoli. It just knows how hard it's being pulled down on. Bless you. Questions? This one feel better? What else is on your minds? Yes.
Can we just do some of the homework problems?
Yes.
Just any of them, I'll have one particular, just any of them.
Well, before I pick one at random, does anyone else have an opinion about a homework question that's been tricky? Give me a second while the basement Wi-Fi remembers my WebStime login very slowly. Feels like it's going even slower than normal out of spite today. Like, look at this. Oh, okay, as soon as I show people, now it works. So, it's just embarrassed. Let's see, let's start, let me look through the chapter 5 homework. That's the most recent one. This is a good one. How about chapter 5, question 1, to start off with? Because this one, I think, summarizes a few concepts together pretty nicely. Here we have a box that is being pushed by a force, and kind of similar to the slide question actually, that applied force is not entirely x nor y, it is pointing at an angle, and kind of a weird angle, because if you want to push something forwards, you really shouldn't push forward and down on it at the same time, but that's what this person is doing. Maybe they're very tall, and it's a very small object, and they're just kind of leaning down on it, sliding it forward. But whatever the reason, they're pointing both forwards and down at the same time. You are told what the mass is, you are told the distance that the box is going to be pushed at. The table is frictionless, which is nice, and the applied force is, everyone actually has 16 newtons. Fun fact about WebAssign, only the red numbers are randomized for each user. If it's not written in red, it's the same for everybody. But everyone else has randomized red text. So if you've been working with your classmates on things and you've noticed the questions are slightly different and you have different answers, it's because the red numbers are random. Which encourages, I find it encourages, my goal is it encourages students to work together in figuring out how to solve things, and then everyone has to do their own math with their unique numbers. Please remember, work together on the homework. Teamwork is good. Anyway, where was I? So everyone's going to have a constant force of 16 newtons at a slightly different angle, and the questions being asked are, determine the work being done by the box, on the box by this force, determine the work done by normal force on the box, determine the work being done on the box by the force of gravity, and determine the work done by the net force on the box. So, let me actually, no, I'm going to keep that there actually. Remind me, what is the formula for work?
Work equals,
Force with the 2 lines.
force parallel times of x.
Very good. The two lines mean parallel. So in order to do work, according to this formula, the force must be parallel to the displacement. What direction, what axis does the displacement point in this question?
The x-axis.
The x-axis. The box is being pushed some distance forwards in the x. So the displacement here is very specifically x-axis. So only x-axis forces are going to do any work in this particular example. I'm going to redraw the box. I'm going to try to figure out all of the forces currently acting on this thing. There's an applied force of 16 newtons being applied at a slightly variable angle for each user. And because it's pointing at an angle, that applied force has both an x component and a forward pointing x component, and also a downward pointing y component. So that one force can be divvied up into those two components. Which component is going to actually accomplish work in this case?
Force x.
The x version, exactly, because the displacement is x-axis, so only the x component of this force is actually going to accomplish any work here. if we were to plug in the y-axis force there, we would have to consider the y-axis displacement of the box. And if it's moving only sideways, what is the y-axis displacement of the box? 0, exactly. It's not moving up or down. So only the x-axis leg here is actually going to accomplish anything. And to prove that, I'm going to quickly work through this to get to that 119 joule answer. For this random assortment of numbers, it's a 20-degree angle and I need the x leg, so ca, one of these markers must have a usable amount of ink in it. Cosine of 20 is going to equal the x leg over the 16 Newton applied force. So Fx is 16 times cosine 20. Again, you will have a different angle there if you are working along with your own version. 16 cosine 20. That's going to be 15.04 newtons forward. So that is the leg of this triangle that is within the horizontal displacement of not 7.9 meters. Actually, I'll put it up here. Delta x equals 7.9 meters. So, according to the work formula, multiply the 15.04 by the 7.9, and that should give us the approximately, 118.7 joules, which rounds up to what the computer's expecting of 119. So that is the work that is actually being successfully done on the box. Skipping ahead to B and C, the work done by normal force and the work done by gravity on this box, why are those answers 0?
Because it's not moving
It's not moving how?
up or down.
It's not moving up or down. So there is definitely a force of gravity and a normal force present, but they are pointing up and down, which is not parallel to the x-axis displacement. So neither of them is doing any work here. And that is why both B and C are 0.
But you can still calculate what force they are working with.
Correct. You can calculate what the force of gravity would be and what the normal force would need to be, but we can kind of just skip straight to the answer of 0 because the displacement up and down is 0.
And since there's no displacement, there's no work done.
Exactly. You can have the strongest force in the world, but if the displacement isn't parallel to it, it doesn't accomplish any work. No energy is successfully used and the task is not actually done if the displacement and displacement and force are not parallel. Sorry?
You do number 3.
On this or the practice test?
This.
This, okay. Any questions before moving on? All right, so chapter 5, homework question 3. Interesting one. Here we have a fired projectile moving very fast, and it is launched into a hunk of wood. I only have so much board space, tragically. Is everyone comfortable if I erase this section? Okay. So initially, we have a very tiny object being launched horizontally at a very massive but stationary object. So here's our initial state. Before doing anything else, what type of energy exists in this initial state?
Potential.
If this object is currently in motion, what type of energy does it have?
Kinetic.
Kinetic, very good. Now, eventually this projectile is going to hit the tree trunk and lodge itself within the trunk. So it's going to burrow out a crater. And after that happens, it is not going to be moving anymore. So it doesn't have any kinetic energy left anymore. Where did that kinetic energy go?
Into the tree.
Yeah, the tree just kind of absorbed it. Technically, as the projectile begins striking the trunk, it will begin exerting a force on it. You could call that a frictional force. You could just call it an applied force. You call it a normal force technically, but whatever it's called, the trunk exerts a force on the projectile, and that force is going to cause the projectile to slow down over time, because that's what forces do. They cause acceleration, and slowing down is an acceleration. And a force applied from the trunk will act over a certain distance. So what's happening here is the trunk is doing work upon the projectile, doing work and taking the projectile's energy away. And really some variation of this happens anytime something slows down, if I'm being honest. When you hit the brakes in your car, it's friction doing the work to slow you down. Here it's the surface you are striking that is doing the work to slow you down. But something always is to do negative work to take away your kinetic energy and cause you to eventually stop. So the two questions here are, using work and energy consideration, So first question is, using work and energy considerations, find the average force that stops the projectile. And what I'd recommend here, since it says use energy considerations, first let's consider how much kinetic energy the object initially has, which would then be equal to the work required to stop it. Because if it has, like say, 1,000 joules of energy, the trunk would have to do 1,000 joules of work to take that energy away and stop it.
Because in a frictionless world, no energy is being lost as the fluid travels.
Correct. But in this world, the projectile has very tiny mass. 7.8 grams would convert to 0.0078 kilograms. And a very fast velocity. Mass number is consistent, but the velocity number is randomized, so do note that if you are working along with your own version. So everyone will have a slightly different kinetic energy. Make sure you are converting that mass properly, but the velocity is already in the units you want. And the initial kinetic energy level of the projectile, it should be about in this range, approximately 1,500 joules, depending on if your velocity is higher or lower than mine. That is the projectile's initial energy level, and the trunk is going to have to do at least this much work in order to stop it. So the work done by the trunk would be equal to the magnitude of this energy level. So the work done by the trunk has to remove this much energy. So work equals force parallel times displacement. As the projectile displaces within the trunk, because as soon as it makes impact, it's going to move a certain distance inside of the wood as it buries itself within a small crater of its own making. It will displace a certain distance horizontally within the wood of the trunk. That'll be the delta x part of the work formula. The work done by the trunk would need to be equal to the amount of energy the projectile is about to lose, and it would take a certain amount of force to actually pull this feat off, and the force is what we're going to solve for. So for work, projectile has to lose 1547.9 joules. Force is unknown, and your displacement is both random and in centimeters, so make sure you properly convert it into meters before using it. And you will get a pretty big amount of force. It will be higher or lower depending on your randomly generated numbers, but expect something in the range of the 20,000s. Tree trunks are pretty good at stopping things. I wouldn't want to run face first into one. I speak from experience. I mean, if a full-grown tree could stop a car in its tracks. So, first question, how do we feel about finding that required amount of force?
You just find the initial kinetic energy,
Mm-hmm.
then that will equal the work used by the tree to stop the bullet, and then simple algebra of time force, or algebra of time force.
Correct. Now, for the second part, assuming that force is constant, determine how much time passes between impact to stop. And actually, I would say this goes back to chapter 4, because I would recommend using net force equals mass times acceleration for this one. We've determined the force that stops the projectile. We know the mass of the projectile, and that means we can figure out the acceleration of the projectile. And acceleration is change in velocity over time. So if we find acceleration, we can figure out how much time it would take it to go from fast to stop. So you would take your answer to the first part, that very large force right there. That would be equal to the projectile's mass, which is also very tiny, times acceleration. And I'm going to kind of go ahead and plug in the acceleration formula here to kind of show how this can be done all at once. Acceleration is change in velocity over time. Velocity is going to change to 0 from, force points backwards. I'm going to put that negative sign there to make everything make sense. It's changing from 630 to 0 in some amount of seconds. So acceleration is change in velocity over time. If I plug that formula in, it just solves straight for time. We are slowing down, so our change in velocity is negative. For that reason, I have made the force negative since it points in the same negative direction as the acceleration. And so, T would have to be brought over there, force would have to be sent to the denominator. Delta T would be 0.066 negative 3 to 630 over negative 24,353.18. And all of this should give you a very, very small amount of time. Because most collisions, and collisions is actually what we're going to be studying first after the test. Chapter 6 will be about momentum, collisions, and what happens to momentum and energy in a collision. They tend to happen pretty fast. Like if you throw, well, I can physically right now, throw something at the wall, so brace for impact. The actual collision part happens in like a nanosecond, right? Like you don't really perceive the start versus the end of the collision. It just happens. So most collisions occur in a very small amount of time. I watched a lot of Mythbusters growing up, probably why I became a scientist. And they would have to do like really high-speed freeze frame video whenever they like drove a remote control car into a wall for whatever reason. And so the whole process of, 60 miles per hour to pancake happens in like a millisecond, as kind of evidenced here by the final answer being 0.00021 seconds, which is 0.21 milliseconds. That's probably faster than you blink. So as far as the human sensory perception is involved, that feels pretty much instantaneous. But it's still technically a fixed amount of time. Like, it is a number of seconds. It's not technically instant. It's just faster than human processing speed, I assume. Questions, opinions, concerns?
If we feel confident on the practice test, do you think we should be good for the actual test?
Yes. I wrote the practice test specifically for that reason, and I also made the practice test longer and more difficult than the test itself. Because I'd rather you make mistakes there than on the actual thing. So, let me know if you need anything.
Sorry, what time is the lab on Friday?
1:30. Lab is always 1:30 every day of the week, Monday, Tuesday, Wednesday, Friday. Thursday is the only day there is no option. Thursday's a myth. A second day that starts with T, has to shape abbreviated to R, come on.
I feel like that's
Come again?
it feels like it's released in me. Where you just
Oh, the